Okay, so let's scoot on. Let's talk about polar coordinates. You know, so far in our mathematical careers, we've been speaking about the rectangular coordinate system, the xy axis, and points on it labeled x, comma, y, correct? And we had different quadrants that we worked with. Agreed? Okay. Well, now that we've gotten into trig, we are going to take our xy axis, and it is going to be, I don't want to say necessarily converted, but we are going to be looking at it in a different format. Just like when we had degrees, we're used to dealing with degrees, but then we get into trig and we have this measurement called radians, correct? Well, now that we're into trig, we can get off the xy axis and put it into a different axis. And this is where the polar coordinates come in, because it's a polar coordinate system. So let me draw some similarities at the same time as I'm talking about the polar coordinates. Okay, so here's our xy axis, right? And when we have an angle, we have the initial side of the angle here with the vertex of the angle there. Agreed? Okay, well, when we get into the polar coordinate system, the initial side is no longer called the initial side. This initial side is now known as a polar axis. And by the way, it is now a ray, and from geometry days. Okay, so this is now your polar axis, and the vertex is no longer called the vertex. The origin is no longer where the vertex is at. This origin is known as the pole. Okay? Now, over here on the xy axis, and let me label it as such, we have the points x, y. Well, when we get into the polar coordinate system, shall I say, our point is no longer x, y. It's r comma theta. Now, you're like, okay, theta is an angle. Yes, theta is an angle. R is a distance. That's what we need to understand. Because we think radius. We see r, we think radius. And I totally get it. But r is the distance from the pole to the point. R is the distance from the pole to the point. Now, when we say distance, distance is always what kind of number? Yeah, distance is always a positive number. So they will occasionally write absolute values around that R to represent distance. Cool? Okay, now, let me just take us off the polar coordinate system for a second. Let's say we have the point r comma theta. So, our pole, right? Here's our polar axis. And if I have the point r comma theta, then that means, say this is the point right here, then that means when I draw this ray, that from here to here, the pole to the point is r. That's your distance. And from the polar axis to where the ray actually ends is your theta. Okay? Now, when we open, just like over here when we're on the xy axis, and we open in the counterclockwise position, we open in the direction of the labeling, this is a positive opening. Okay? But sometimes you have points where they are a negative r comma theta. Now here's what the negative means. What it means is this. It means it's exactly opposite this ray that has a positive radius. So, for instance, if I was graphing this point, negative r comma theta, I would still open theta amount. But because it's a negative, that tells me that the ray I'm actually looking for is down here. This would be the absolute value of r. This would be the same distance as this distance. Okay? And by the way, since this is already positive, let me get rid of these absolute value signs because we don't need them here since the r was already positive. But I'll put it down here because I was graphing a negative r comma theta. And this opening is still the same theta. These two are exactly the same theta amount. It's just now, since it said negative r, instead of going in the counterclockwise position, I go in the clockwise position. And since this ray with the negative r is exactly opposite the one with the positive r, this is a 180-degree angle, if you notice. Right? This is a 180-degree angle right here. So when you know where r comma theta is, you know exactly where negative r comma theta is. By the way, theta can be in degrees or radians. So just know that. Theta can be in degrees or radians. So hang in there. I'll be right back with more information. Okay, so let's plot some polar points. Now, I'm not going to look at the entire polar coordinate system. For right now, I just want you to get the hang of plotting points off of that polar coordinate system so you can see what it looks like. So then it's easier to put it back on the system, okay? So the first point I'm going to plot is the point 3, 90 degrees, okay? So remember, 3 is the distance from the pole to the point. And 90 degrees is the angle, and the angle could be in degrees or radian measurements. So here's the deal. First and foremost, I'm going to get the pole down, and then I'm going to get the polar axis down. So what works best for me is this. I am going to look at the angle first. That's the easiest way for me to plot these. So since this is a 90-degree angle, I know that I'm going to end up right here at 90 degrees. Okay? And since this 3 represents the distance from the pole to the point, then I'm just going to put these marks in. They're not really tick marks like on an XY axis, but they'll do for right now. So this is where that would be. This point would be where 3, 90 degrees is at, because this distance would be a distance of 3. Good? Okay, let's look at another one. Let's look at 4, 270 degrees. Okay, so same thing. I need the pole. I need the polar axis, and if you allow me to label it PA for polar axis, okay? First thing I look at is the angle. So we're going 270 degrees. So from the polar axis, I'm going around 270 degrees, which means, right, this is where we're at. And now, since that is a 4, that is the distance from the pole to the point. So right here. This is a distance of 4 from the pole to the point. So this is where the point 4, 270 degrees is located. Good? Okay. No surprise, got another one. Let's look at 2, negative 5 pi over 4. So again, I need the pole and I need the polar axis. And in this case, the angle is a negative 5 pi over 4. And negative means I go in the clockwise direction, right? So I go in the clockwise direction, and negative 5 pi over 4 kind of ends up in quadrant 2, doesn't it? So you still have to know the quadrants and where these angles will end up at in order to correctly graph polar points. So this is negative 5 pi over 4. And it has a distance of 2. So right here is the point 2, negative 5 pi over 4. And right here is a distance of 2 from the pole to where the point ends up. Good? Okay, hopefully you're getting the hang of it. Got another one for us. The point negative 2 comma 0. Now remember, I'm in polar coordinates. Polar coordinates. So be very careful about this. This is polar coordinates. So I got the pole. I have the polar axis. Whoops. PA. Right? Okay. So 0 tells me 0 radians. So I'm not going anywhere. I'm staying right there. And if this had been a positive 2, then the point 2, 0 would have been, sorry about that, then the point 2, 0 would have been here, because this would be a distance of 2, and that would have been the point 2, 0. But because the r is a negative 2, then that means that I go in the exact opposite direction. Remember, this is going to end up being 180. From the positive r. This is where your negative r would have been. And you're like, well, that doesn't look any different than had it been on the xy axis. I get it, but hang in there, because I've got some more examples for us on plotting polar coordinates. Okay, so let's look at this next point. So remember, in order to graph it, you need the pole, and then you need the polar axis, right? Now, this has an angle of pi, which means I would have ended up over, which means I should go this direction, pi, right? And then the distance that the point is away from the pole is 3 spaces, shall I say. So this would have been the point 3 comma pi. But because the distance is a negative 3, then that means I go in the exact opposite direction from the positive 3, which means in reality, the point that I'm looking for, or I'm supposed to graph, is over here. This still has a distance of 3 spaces, but the negative tells me I need to be in the exact opposite direction from the positive 3 comma pi. Remember, now this has a distance of 180 degrees. Good? This is where negative 3 pi is located, right here at this point. Got it? Okay. When they have the negative distance, I always graph it as if it was a positive distance, and then I can better see the 180 degrees away to get the negative distance. Let's look at another one. Let's see if we follow along. So negative 2 comma 135 degrees, right? Okay, so again, you need your pole and you need the polar axis. And 135 degrees, you know, would be in second quadrant over here, right? So technically this is 135 degrees. And since it has R, this is where the point positive to 135 degrees would be, correct? Because this is a distance of 2 spaces. But this isn't a positive 2, this is a negative 2, which means I need to go in the exact opposite direction by 2 spaces. Right here, this still has a distance of 2, but now it's a negative 2, comma 135 degrees. This is exactly 180 degrees away from where the positive 2, 135 degrees would have been. Are you with me? Okay, again, graph the angle first and then do the positive distance. Once you have that, then you go 180 degrees away from that point, and that's where the negative distance would be located. Got it? Okay, let me get another one down. Okay, negative comma, negative 3 pi over 4. Again, get the pole down, get your polar axis, right? And I'm going with the angle first, negative 3 pi over 4. Which quadrant would that have been in? Yeah, that would be here, basically 4th quadrant, wouldn't it have been? And I would have gone a distance of 3 from the pole. So right here, this would be the point 3 comma negative 3 pi over 4. But because the r is negative, that means from this point I'm going to go 180 degrees away in the negative direction and still have this r, this distance from the point to the pole, be a distance of 3 spaces. This is where the point negative 3 pi over 4 is located. Cool? Right here. This is where it would be, in this point. Good? Okay, let me get another one. I think I mislabeled my numbers. I think this is number 8. But anyway, you get the hang of it. Okay, so again, the polar axis, this negative angle, that's what I'm going to graph first. So this is a negative pi over 3. And I would be a distance of 1 from the pole. So this is where the point positive 1, negative pi over 3 would be located. But because it's a negative r, that means I'm going to go exactly 180 degrees in the other direction. So this is where that point, negative 1, negative pi over 3, is located. Cool? Are you with me? Okay, so again, I always graph the angle first and the positive r. And if the r is negative, that tells me I'm going to go exactly 180 degrees in the other direction to find the actual negative r, comma, theta point. Cool? Okay, hang in there. Okay, so just like we dealt with our angles that were quadrant 1 angles, those quadrant 1 angles had other names in quadrants 2, 3, and 4. Correct? Like 30 degrees was also known as 150 degrees in quadrant 2, and 210 degrees in quadrant 3, and 330 degrees in quadrant 4. Well, our polar coordinates also have other names that they go by. So here's the deal. The directions say they want us first to plot each point and then find the other polar coordinates given based upon these 3 problems, these 3 attributes. So I'm just going to relabel this very quickly. So let's look at number 1. They said plot it first. So when I plot this, we have our pole, we have our polar axis, and we're supposed to go 2/3, and it has a distance of 5. So this is 5 comma 2 pi over 3. Good? All right. So this distance from here. Now, let's take a look at this first part, part A. It wants r to be positive, but notice theta is between 0 and negative 2 pi, right? Which means this is going clockwise. It's going against the labeling of our xy axis. So the two, you kind of have to keep the two in mind because it helps. The xy axis system still helps us understand which direction we should be going. So this means that theta should be negative, should be less than 0. Are you with me? So now, let's think about this. If I'm supposed to end up at this same point, r is already positive, so I don't have to worry about it, right? But if I'm supposed to go negative, that means I am going in this direction, and I'm supposed to end up here, aren't I? Now, for simplicity's sake, let's do this. This is pi, isn't it? So this is a distance of pi. From the polar axis to right here is a distance of pi. Remember those reference angles we dealt with? Oh yeah. So the reference angle between pi and where this ended is negative pi, isn't it? Because if I take pi and subtract pi over 3, don't I get 2 pi? Okay, so here's the deal. When I go in the negative angle direction, there is negative pi plus an additional negative pi over 3. So I still have 5, but now it's negative 4 pi over 3 because I went pi, negative pi, and an additional negative pi over 3. So a negative 1 and an additional negative 1/3. With me? Okay. Let's look at part B. Part B wants the radius to be negative and your angle to be between 0 and 2 pi. So that's the traditional circle, one rotation around the circle, so that wants it positive, right? Okay. So remember what we said. Here is 5, at positive 5 and 2/3. Well, if they want the r, the distance, to be negative, that means it would go in this direction 180 degrees basically, right? Okay, so think about this. Same deal. This is 0 radians, and from the polar axis down to the opposite line has a reference angle. What's the reference angle? Yeah, the reference angle is the same. The reference angle is negative, right? Pi over 3, isn't it? So, oh, pardon me. That's what my brain was also thinking. This is also 2 pi, isn't it? So, my r is supposed to be negative. Well, that's the easy part. Negative 5, right? But now my angle is supposed to be what right here? Well, if you take 2 pi and subtract pi over 3, what do you get? Yeah, you get 5 pi over 3. That would be the name of this particular angle that has a negative r and a positive theta. It would be over here. That would be the exact same as this one. Good? Okay, and there's a part C. And part C wants r to be greater than 0 and theta, theta is also greater than 0, but theta really is greater than 2 pi. Because when they say 2 pi to 4 pi, that means they're in the second rotation of the circle. We've gone around once, and we've gone around a second time. So, the r being positive, well, we got that. That's 5. But if they want it greater than 2 pi, that means here's my initial, and I have to go one more time around the circle. So you're going to take 2 pi over 3 and add to it another 2 pi, which gives you 8 pi over 3. Good? Okay. This might still be the one you're having a challenge with. Here's the deal how I got this angle again. I took 2 pi and minus the reference angle. That's how I got that 5 pi over 3. Got it? Okay. And some of you may be asking about this negative 4 pi over 3. Remember, I want pi and an additional pi over 3 to get there. Okay, let's look at the second one over here. First thing they want me to do is plot it. So when I plot it, my polar axis, right? Negative pi over 4 goes this direction and out 3. But since this is a negative 3, it'll be in this direction, won't it? And this would be where your negative 3, negative pi over 4 would be located. Because it's exact opposite of here. This is where it should have been. So, understand something. This is a reference angle of negative pi over 4. Because here was negative pi over 4. And these are supposed to be exactly the same. They're supposed to be 180 degrees away from each other. So if this was negative pi over 4 from this x-axis, then this is negative pi over 4 from this x-axis. And I'm putting x-axis in quotes because I'm not technically on the x and y-axis system, yet understanding the x and y-axis system still helps me with this. Okay, so here's the point. That was the first thing they wanted me to do, was plot the point. Done. Part A wants us to find the name of the point when r is greater than 0 and theta is less than 0. Theta is negative. Well, I think we almost have that one because I already know that r greater than 0 would just be a positive 3, wouldn't it? Now, theta has to be between 0 and negative 2 pi, right? So remember, I need to end up at this point. So if I go from this 0 radians, or also known as 2 pi, to end up at this same point, I need to go pi and an additional pi over 4, which tells me it's at negative pi over 4. Got it? It's at negative pi over 4. The same, I need to be right here at that same point. Part B. The radius is positive and the angle is positive. So both of them are positive. Oops, I'm sorry. The radius is negative. Sorry. Good thing I took a second look there, right? Okay, so the radius is negative, and then theta is positive. Okay, so radius being negative, that's still going to be a negative 3. No problem. But now my r is supposed to be positive. So here's the deal. That negative 3, remember, meant I went 180 degrees in this direction. Because this should have been where it was, right? Which means I'm going to go around the circle to end up here. And this is 2 pi minus pi over 4. That ends me up at 7 pi over 4. Just like over here, I took 2 pi and I subtracted the reference angle. Same thing. Over here, I'm going to take 2 pi and subtract that reference angle so I can get the positive angle, which is 7 pi over 4, because 7 pi over 4 is the same as a negative pi over 4. Got it? Okay. Part C. Let me grab some board space. I'm going to use this board space right here. And now this part C is with problem number 2. Okay, so I need the radius to be positive and I need theta to be greater than 2 pi. Well, the distance. R is the distance. So that's definitely a positive 3. Now, your angle is supposed to be between 2 pi and 4 pi. So that's the second rotation around the circle, isn't it? So here's the deal. This point right here, this angle measurement right here has a negative pi over 4 reference angle, which means this would have a value of 3 pi over 4 going in the positive direction of the angle. Agreed? So I need one more rotation around it, which means I'm going to take that 3 pi over 4 and add to it one more circle rotation, which is how I get 11 pi over 4. Cool? Hang in there. I got 2 more examples of this. Okay, let's look at this third problem. Same directions. First thing they want us to do is graph it. So when we graph it, here's the pole, here's the polar axis. We would have gone negative 2 pi over 3. And this would have been, right? This would have been positive 2, negative 2 pi over 3. But they don't want the negative 2 distance. They want a positive 2, they don't want a positive 2 distance, they want a negative 2 distance. So here's where this point ends up, right? Negative 2, negative 2 pi over 3. Good? Okay. Now, part A. Part A wants us to find another name when the distance is positive and the angle is negative. Right? Okay. So, let's think about this a second. If I want to end up here, this has a reference angle of pi over 3, doesn't it? If this is supposed to be a positive r, well, that's going to be 2. If they want to be here, and we want theta to be less than 0, then it's not going in the counterclockwise direction. We have to go opposite that. So when we go around the circle, this amount to end up here, I have basically 2 pi, right? And I'm going in this negative direction, which means I end up at negative 5 pi over 3, because that's the distance, pi over 3 minus the 2 pi. That's where I'll end up. If I take pi over 3 and minus the 2 pi, that'll give me the negative 5 pi over 3. That's where I want to end up. Cool? Okay. The second part wanted your distance to be positive and your angle. I did that last time, didn't I? I guess I just want that positive r. Okay, we want the distance to be negative and the angle to be positive. Okay, so the distance to be negative. Well, there's your negative 2. But now I need the angle to be positive, right? Which means I am going to go, if I'm going to end up here, I'm going to go around the circle. This is pi, and an additional pi over 3. This gives me 4 pi over 3. Remember, I take the 2 pi and I subtract the negative 2 pi over 3. That's how I'm going to get the positive angle right there. Cool? Okay. And then last but not least, part C. Part C wants the distance to be positive and your angle to be greater than 2 pi? Well, the distance to be positive is just going to be 2. If I take your angle measurement of pi over 3, because this is where it's at, and I add one more rotation around it, that'll end up at 7 pi over 3. 2 pi plus another 1/3. This is going to be 2 pi plus another 1/3, because there's the 1/3. Got it? This was 2 pi minus the 1/3 to get me here. And this one was going half the circle and an additional 1/3 to get to here. Good? Okay. Let me get another one down for us. I know you may have to go back and rewind this section, so to speak, about plotting these and finding the other names. Do so, okay? It's not as bad as you think, but just understand you have to visually see where things are happening. Okay, so let's look at this one. So they want us to plot it. So there's the pole, there's the axis, right? We're going to go 3 pi. Well, that's one rotation around the circle, and then it should have ended up over here, right? With a distance of 2. But they didn't want to be over there because the radius was, not the radius, the r was negative, which means right here is where the negative 2, 3 pi is. Okay, so the first question to find a new labeling is the distance to be positive. Well, that's easy. That's just a 2. Now they want this negative, don't they? Well, if they want this negative to end up here, don't I go like one full circle? Doesn't that end up at negative 2 pi? Good. The second part wants that distance to be negative and wants my theta to be positive. Well, the distance to be negative, well, that's negative 2. Got it. But if I want my theta to be positive, remember, to get back over here, this is the one you're looking at. This would have been just pi. Boop. And last but not least, they want the radius to be positive and they want your angle to be greater than 2 pi. Or equal to 2 pi. Remember, these are also equal. If you go back and look at the slide before this, so to speak. Okay, so this is going to be 2, and this just ends up right at 2 pi again. So this number 4 wasn't too bad. Why? Because we were on the axis itself, so it wasn't too bad. It's these guys you kind of have to wrap your brain around a little bit. So I would rewind this and look at the first 2 problems and this third one especially to help you with the other names. It's all visual. It really is. Okay? And understanding that sometimes you have to take your 2 pi and minus the reference angle, or you're going pi and adding a reference angle. Got it? Okay, so we're going to head into converting polar coordinates to rectangular coordinates and vice versa. So hang in. Okay, so now we're going to convert polar coordinates to rectangular coordinates. But before we actually get into the conversion, there's a couple things I need you to remember. One thing I need you to remember is that the cosine of theta was equal to x over r, wasn't it? And the sine of theta was equal to y over r. Agreed? Why am I bringing these up? Because these have the x and the y in them that I need for rectangular coordinates, and this has the r and the theta I need for polar coordinates. So knowing or remembering how to write cosine of theta and sine of theta brings together the r and the theta for polar and the x and the y for rectangular. Now, in this one, if I solve for x, x would be equal to r times the cosine of theta. Agreed? And over here, if I solve for y would be equal to r times the sine of theta. So notice, when I solve for x, I have the r and the theta on the same side. Those are polar, aren't they? And when I solve for y, I have the r and the theta on the same side, and that's also polar stuff, isn't it? Okay, so let's look at a problem. Let's look at 3 comma pi over 2. Now remember, this is your r and this is your theta, isn't it? And I want to write it as x and y. I want the rectangular coordinate. Well, to find x, we already have it. X is supposed to be r times the cosine of theta, which means in this case to find x, I'm going to take the r, which is 3, and multiply by the cosine of pi over 2. Well, you have to remember the cosine of pi over 2. What is it? Good, 0, which means x is going to be 3 times 0. So x is just going to be 0. So I have the first coordinate for rectangular. X is 0. Let's go find the y. To find the y, I'm going to do r times the sine of theta. Well, y then is going to be 3 times the sine of pi over 2. Remember what the sine of pi over 2 is? Good, I heard you. 1. So this is 3 times 1, which is just 3. So there is your y coordinate. So you're telling me the polar coordinate of 3 comma pi over 2 converts to the rectangular coordinate 0 comma 3. Cool? Okay, let's look at another problem. Let's look at -2 and 3 pi over 4. All right, now I need to find x and I need to find y. So to find x, I'm going to take the r and multiply it by the cosine of 3 pi over 4. So remember what the cosine of 3 pi over 4 is? Yeah, isn't that equivalent to a 45-degree angle? And cosine and sine on a 45-degree angle is pretty easy to remember because they're exactly the same, aren't they? Good. Square root of 2 over 2. But now remember, 3 pi over 4 is a quadrant 2 angle, which means your cosine is negative and your sine is positive, which means this is going to be multiplied by negative square root of 2 over 2. So x is just equal to a positive square root of 2, isn't it? So there is the first part of your rectangular. The y is r, which is -2, times the sine of 3 pi over 4. Well, that's right. Sine of 3 pi over 4 is the same, square root of 2 over 2, and in quadrant 2, sine is positive. So that will be negative square root of 2. So here is your polar, here is your rectangular. Easy peasy? Good? Yeah, this isn't too bad to convert this direction. Now let's look at the other direction. Let's go from rectangular to polar. Okay, so now they want us to take rectangular coordinates and convert to polar. So I need to go from x, y into r and theta. Are you with me? So here's the deal. Here's x, here is y. We need r and theta, don't we? Well, here's the deal. I can find one of those variables very quickly. If I remember I'm dealing with an x and a y, don't I have an equation that deals with an x, a y, and an r? Yeah, good old Pythagorean theorem, right? For the trig part, isn't it x squared plus y squared equals r squared? Right. So here's the thing. I can actually find r first. And to find r, I need to remember Pythagorean's theorem. So, x squared plus y squared equals r squared, right? So we have 1 plus 1 equals r squared. We have 2 equals r squared. That's an r. Sorry about that. Which means r equals square root of 2. Now remember, you take the square root, you get 2 answers. But r is a distance, and that's supposed to be positive. So remember that. So r is always a positive answer. So square root of 2. Got it? Okay, now I need to find theta. Well, here's the deal. I now have x equaling 1, y equaling -1, and r equaling square root of 2. If I have those 3 pieces of information, couldn't I use a trig function to help me find theta? I certainly could. So here's the deal. I'm just going to use cosine. You could have used sine, you could use tangent. It doesn't really matter. Some people prefer tangent because it just deals with the x and the y. So in case they messed up on r, it won't make a difference. So if I look at cosine, that's 1 over square root of 2, right? Which if I rationalize it is square root of 2 over 2, isn't it? Aha! Which means that if the cosine of theta is square root of 2 over 2, that means my theta is, you're like, theta is 45 degrees. Hold on. Your reference angle is 45 degrees. And you're like, why reference? That point is located in which quadrant? Yep, this is a quadrant 4 point. Positive x, negative y, that's quadrant 4, which means the theta I'm looking for needs to be in quadrant 4. So the theta would be, good, 315 degrees, which means, now that you have r, now that you have theta, this point converts to square root of 2, comma, 315 degrees. Cool? And if they want this in radian measurement versus degree measurement, then rewrite 315 degrees in radian measurement. That makes sense? Okay, got another one for you. How about we look at -3, comma 3. Okay, we need to find, right? We still need r and theta. Which one do we find first? R. So, to find r, we're going to use Pythagorean's theorem, which basically gives me 18 equals r squared, right? Which means r is equal to 3 square root of 2. Agreed? Okay, so here's what you're telling me. Right now you're telling me x equals -3, y equals +3, and r equals 3 square root of 2. Right? Okay, can we find theta? Yes, we can. So, to find theta, I'm going to use cosine. You can use sine, you can use tangent. Most people will not use secant, cosecant, or cotangent. So, cosine is x over r, which looks like cosine reduces to -1 over square root of 2. Aha! That looks familiar. That looks like the reference angle of 45 degrees again, right? However, what quadrant are we in? -x, +y, we're in quadrant 2. Which means theta is 135 degrees. Which means your angle will be, r is 3 square root of 2, and theta is 135 degrees. This converts to 3 square root of 2 135 degrees. Cool? Okay. Guess what? We're going to be converting between polar and rectangular equations now. Okay, so we're going to convert polar equations to rectangular equations, which means we need the r and the theta to be gone, and we need x's and y's. Now, some things to remember. We need to remember this Pythagorean formula for x squared, y squared, and r squared. We need to remember that x is equal to r cosine of theta and y is equal to r sine theta. These are some things to remember. Now, we are going to accomplish this conversion normally by multiplying both sides by r or squaring both sides. It just depends what we have. And sometimes you'll be like, well, how do I know which one to do? Okay, so let's take a look at this. Let's take a look at number 1. And we want to get rid of the r and the theta because we need x's and y's. So here's the thing. We can either try multiplying both sides by r or squaring both sides. And you're like, well, which one do I try? You know what? Try the first one. Let's see what happens when we try the first one. Maybe the first one works. Yay! And maybe it doesn't, which means I'll go to the second one and I'll square both sides. Cool? Okay. What I'm noticing, though, is I can't really get rid of the sine of theta yet. If I get rid of the sine of theta, I could write it as y over r, couldn't I? So, hang in there. Sometimes there's 2 and 3 approaches to the same problem, but if we stick with one of these two, it usually will help us out. So I am going to take both sides, and I am going to multiply by r. When I do that, that'll give me r squared equals r sine of theta plus r, won't it? Okay, so now I can rewrite r sine of theta. R sine of theta can be rewritten as, y. So I can write r squared equals y plus r, couldn't I? Good. Now, r squared can be rewritten, can't it? Yeah, it's the same as x squared plus y squared, isn't it? So x squared plus y squared equals y plus r. So far, so good. But this r still needs to go, so I just need to get rid of the r. You're like, well, how do I get just r? Well, right here, here, and here. If I get r by itself, right, then I'm going to have y over sine theta, and I bring back a theta, which I don't want to do. Here, if I solve for r, it's going to be x over cosine theta, which means I bring a cosine theta in, which I don't want to do because I don't want theta. Here, if I get r by itself, I take the square root, don't I? And it's just of x's and y's, isn't it? So that's what I'm going to do. I am going to rewrite r as, and the reason I can do that is because if I square root both sides here, that side stays together. If I square root both sides, I am going to get the square root of x squared plus y squared. It's not a very nice looking equation, but that's what we have. This is the polar form. This is the rectangular form of it. This is the conversion. Cool? And I know some of you may be thinking, I think I'd rather leave it in polar form. It looked a little nicer. Totally get it. Okay, y'all with me? Good. I got a second one for you, and I want to leave this information up here. So give me a few moments. I'm going to erase this. And you know, as always, please make sure you rewind if you need to go back and go, wait, what did she say? Because gratefully you can rewind and pause, can't you? All right, so let's look at the second one. The second equation we're going to convert is r equals 4 over 1 minus cosine of theta. Got it. Now, some of you are like, what am I going to do with that? Okay, well, most of you don't like the denominator anyway, so how about we just get rid of the denominator? So r times, right? That looks a little better, doesn't it? Okay, which means I could distribute, couldn't I? So r minus r cosine of theta. Agreed? Now, we dealt with r in the last problem. R can be found by taking the square root of both sides, can't it? So that means we have the square root of x squared plus y squared minus r cosine of theta, right? And I can rewrite the cosine of theta as just x. Right? Okay, so now you can leave it this way, but sometimes the authors of the book, they solve this a little bit differently, or I should say they convert it a little bit differently. So our answer looks a little bit different than theirs. Let me just show you an extra step or two that you could do, because as I said, the authors of the book may have solved it differently. If I take the x to the other side, this would be 4 plus x, wouldn't it? Right? I could square both sides then, couldn't I? Remember, these are some extra steps I'm showing you that the authors of the book could actually do, because their answer may be a little different than this. If I square both sides, wouldn't I get x squared plus y squared equals 4 plus x squared? And then this can be distributed, right? Which would give you what? 16 plus 8x plus x squared? Do you notice the x squareds drop out if you subtract them from both sides? Which means you have y squared equals 16 plus 8x. So, I know you're asking, well, when do I know to do this? So here's the thing. The last problem, squaring everything, would not have looked so nice, because I would have had too much stuff going on. But this one, if I move the x over and square it, it actually turned out to be a very simple problem to work with. But if it gets too complicated when I'm trying to get rid of a square root, then we're probably not going to do it. And I know that's a little ambiguous, and I'm sorry that it is. But I know for sure this is the answer that the authors have, because they approached it differently than how we approached it. But we end up with the same answer as long as we decided to get rid of the square root, because it was pretty simple to do. Okay, so hang in there. We're going to go in the other direction. We're going to convert rectangulars to polars. I'll be right back. Okay, so let's go backwards. Some of that information that we had to remember in the last problems when we were converting, we need to remember now. X squared plus y squared equals r squared. X equals r cosine theta. Y equals r sine theta. Remember those, because those are going to be important for us here also. So let's look at number 1. I'm going from rectangular to polar, which means I need to get rid of the x's and the y's. What do I know? Yeah, I know I can replace x. X can be replaced with r cosine theta, can't it? And I know I can get rid of the y. The y can be replaced with r sine theta. Agreed? So when you do this multiplication, you get 2 r squared cosine theta sine theta equals 1, don't you? Like, hey, that was easy. That was easy. But I need you to see an observation, and I'm going to do a rewrite. R squared times 2 cosine theta times sine theta, right? All I did was I switched the order of the 2 and the r squared, and with multiplication you can do that, can't you? Okay, 2r cosine theta, 2 cosine theta times sine theta is actually an identity that you need to keep in your memory banks. This is the sine of 2 theta. So this rectangular equation converted to r squared sine of 2 theta equals 1. Good? Let's look at this one. Okay, X squared plus y squared equals? Good. R squared. X equals? Good. X equals R cosine of theta, doesn't it? Now in this case, I'm going to simplify by dividing both sides by r, which means I get the equation r equals cosine theta. Good? Okay. As I suggested before, if you need to rewind this video at any point, please rewind it and make sure you stop and pause where you need to in order to glean the information. So you have fun with polar coordinates, and I'll catch you on the flip side.